Thank you for the invitation to present at this CVPR workshop. My name is Daniel McDuff. I'm a principal researcher at Microsoft. And today I'll be presenting about our work building computer vision tools for recognizing cues associated with both internal and external expression of affect. The types of applications that we're most interested in revolve around health and well-being. And it should hopefully become obvious how some of the things that I'll present could be applied in the context of applications such as telehealth, ubiquitous health and well-being measurements such as fitness applications, but also more broadly in applications such as gaming and also productivity. I'll focus primarily in this presentation on the sensing aspects of our work, aiming at creating ubiquitous health and well-being sensing platforms for everyday devices. And in particular, we're doing a lot of work to optimize these to run on device to create applications that preserve privacy and also improve user experience. The types of signals I'll be talking about are primarily physiological and facial, and these include measuring cardiac signals like heart rate and heart rate variability, pulmonary signals like breathing and respiration, and facial actions. In terms of the vital signs that we're interested in, as I mentioned, these are primarily cardiopulmonary signals, as these can be measured through computer vision tools. We've already done work looking at measuring pulse or heart rate variability, respiration, blood oxygenation, and also there's some interesting work looking at detecting things like arrhythmias and other abnormalities in the pulsatile waveform. Going forward, there's compelling and exciting work looking at ways that we can measure blood pressure or correlates of blood pressure using some of these techniques. And as imaging hardware develops and we get new forms of cameras that can measure beyond perhaps the RGB spectrum, then there's the hope to capture additional pieces of information, such as perhaps body temperature, and then maybe some of information about the composition of the blood through glucose, etc. But to give you context, here's an example video showing two subjects where we're analyzing the RGB video, and you can see the pulsatile waveforms captured via a contact sensor and via the camera. In this second example here, you see two other videos where the input is captured via near-infrared camera. In both cases, you can see that the camera-based measurement can get pretty high alignment, particularly in the RGB space with the contact sensor, even in the presence of facial expressions and head motions. So we can, in a contactless way, just using a regular RGB camera, we can capture these signals. And near-infrared is a little more noisy. In this case, the models were trained on RGB data and then tested on near-infrared videos. But this provides the possibility of measuring in low light conditions, such as for a baby monitor or driving scenarios. In addition to measuring physiological signals, I'll also be talking about measuring more external expressions of affect, and typically for this we use facial action units as a taxonomy for describing the displays expressed on the face. In addition to tracking facial action units, typically we'll look at head motions and other types of behaviors in order to quantify overall activity levels and things like that. One of the things I want to focus on a lot in this presentation is how we're using synthetic data to train these systems. In the past, we relied entirely on video data sets, which were time-consuming to collect, involved bringing people to a lab, recording videos of them under various conditions, and in the case of training physiological measurement systems, involved collecting ground truth physiology via contact devices. And this, again, this is very time-consuming. It requires a lot of cost and effort. Moving forward, we are moving to use a lot more synthetic data where we render avatars using graphics tools to create data that is high fidelity, but we can also control many of the parameters such as the background conditions, the lighting, head motion, facial expressions, as well as superimposing physiological changes driven by real pulsatile and respiration waveforms. To give you an example of what that pipeline looks like, when constructing these avatars, for each frame, we augment the base color and subsurface scattering parameters for the skin texture on the avatar using information about the pulse or respiration signal. And then we also control the motion, particularly of the torso of the avatar, using respiration information to capture motion due to breathing. We can then also drive the avatar using information about head pose or facial actions that we want them to exhibit in these videos, and augment different background or lighting conditions. And this allows us to create many videos very scalably. The nice thing about synthetics is that it also gives us a lot of additional information. So we not only get the RGB videos of these avatars, but we also get high fidelity ground truth about things like depth, segmentation, landmarks, surface normals, etc. And then using this pipeline, we can create many thousands of videos of avatars under different conditions. Of course, with this high fidelity ground truth, not just in terms of depth and segmentation, but also the physiological changes that we used to drive their creation. And these can be used as training data sets. Typically, the models that we're training from a computer vision perspective are based on optical principles. When looking at measuring physiology from video, typically what we're trying to do is recover subtle changes in light reflected from the body due to the physiological processes, and separate these from other types of changes in pixel intensity due to head motion or ambient lighting changes. In doing so, we really want to capture the changes in diffuse reflection, which are typically contain the strongest, for instance, pulsatile waveform. One such model that we've created to do this is the multitask temporal shift attention network. So this model takes as input a series of frames, and we help the network to recover subtle changes in pixel intensity associated with the physiological information by giving it as one input a motion representation, which is essentially the difference of two successive frames. You can think of this as almost as an optical flow type of representation. And then a separate appearance branch which takes as input the current frame of video. And this appearance branch helps drive an attention mechanism so that the motion branch can focus on the relevant regions of the image corresponding to, for instance, skin, which we know, of course, will have a higher pulsatile information than clothing or other regions of the video. One important thing to note about this network is that we typically train it with the derivative of the pulse or respiration waveform. Because we're providing as input this motion representation, and we find this is particularly successful at helping us learn the physiological changes from the video. Another Another innovation here is to leverage temporal shift modules in order to reduce the computational load of this network. So we could use 3D convolutions here to capture temporal and spatial information, but that can be very computationally expensive. And when our goal is to run these algorithms on device, it's not very practical. The temporal shift modules do a really good job at capturing some of this temporal information alongside the spatial information while really reducing the overhead in terms of computation. In terms of synthetics, we've tried several different ways of training our networks. One is to combine synthetic data with real video data in our training sets, train our network, and then test, of course, on real video data sets. This tends to be the most successful. Training only on synthetic data still leads to a sim-to-real gap that we're working on addressing. But when we combine real video and synthetic video together in the training set, we typically get results that outperform just using real videos. And as we increase the number of avatars that we synthesize and scale that, we see fairly consistent improvements in terms of reduction of heart rate estimation error and improvements in signal-to-noise ratio of the underlying waveforms. So the synthetics pipeline gives us this way to continually generate more and more data and improve the robustness of our algorithms. Of course, there is some saturation point. As you can see in these graphs, you get diminishing returns with larger and larger numbers. But as the synthetics pipeline becomes more robust and developed, I think we'll see that we can push these numbers down or up with larger and larger numbers of synthetic data. We have a couple of open source toolbox, one in MATLAB and one in Python, that you may be interested to look at if you're starting out in this space as a way to get familiar with some of the existing methods. In terms of results, here's a comparison of heart rate mean absolute error across one of our video data sets for different methods, starting from our early methods using unsupervised signal processing techniques, which is represented by ICA here, all the way through to our latest work, which was presented at NeurIPS last year. And you can see we've been able to reduce heart rate error from close to 6 beats per minute error to under 2 beats per minute error across this relatively large data set. And this is thanks to including, for instance, the temporal shift modules, as well as using things like synthetic data and being able to train in multitask manner. In terms of respiration, we see similar improvements, a little less dramatic. Respiration measurement is slightly harder, or it's easier to do with more basic methods and harder to get improvements with more complex methods, just because the motion signal typically is slower than the pulse signal, and that makes measuring it accurately over shorter time windows just more challenging, particularly from a frequency estimation perspective. We've worked hard to reduce the latency of these models while maintaining the performance in terms of accuracy or error. And you can see the multitask temporal shift convolutional attention network highlighted in yellow really provides a nice trade-off. And we can get that running close to 150 frames per second while maintaining pretty low error rates. One thing we're doing now with these models is to create apps using them that we can deploy longitudinally to start to look at how non-contact measurement could be used for understanding health and well-being. So you can imagine this as a fitness tracker or well-being tracker for your laptop or for a device that has a camera. And we're measuring pulse, respiration, HRV information using these vision techniques, and then also combining that with information about facial expressions. And then participants that opt in can then track this data on their machine longitudinally to look at affective diurnal patterns. And I'll show some examples of those later. The longitudinal deployment typically involves people installing this software at their workstation. And again, it's privacy preserving in the sense that we can compute these things locally, but they can also be streamed to the cloud for sort of further or more aggregated analyses if that's something that we need to do as part, for instance, of a research study. One thing that we've found is pretty strong evidence of diurnal patterns, both in terms of expressed affect, but also physiological changes. So what you can see in this slide is a few graphs showing the average day for a number of participants who've opted into our studies. You can see in the top left-hand corner the average number of hours in which we detected a face in front of their workstation. So that's just showing kind of the rhythm of the day for most people. This was pre-COVID, so they're coming into the office. They tend to be in front of their workstation in the morning, then they may leave around lunchtime, and then come back in the afternoon, and then typically leave the office around 5 p.m. Looking at facial expressions, we see peaks in positive affect in the morning and the afternoon, and a dip in the middle of the day. And this is likely to be due to essentially energy levels. So as people have lower sugar levels, they're less likely to express positive affect. After lunch, they get a boost in energy, and that's likely to increase expressions of positive affect. Negative affect shows a much more sort of linear increase or monotonic increase across the course of the day. And we think that this might be due to just increases in tiredness and again energy dropping across the course of the day, meaning people are more likely to express negative affect, frustration, things like that. In terms of physiological signals, we see diurnal patterns in heart rate that are very consistent with prior work. That heart rate tends to be lowest at the beginning of the day, peaks right in the middle of the day, and then drops again towards the end of the day. What's interesting is that these diurnal patterns are quite highly correlated with things like cortisol levels. And so you can see here an example from prior work where the same diurnal pattern in heart rate, where heart rate is lowest when you wake up in the morning and then highest towards the middle of the day around 1 or 2 p.m. And this is in part due to cortisol levels dropping throughout the day. And so we're really interested in seeing if we can detect essentially disruptions in these diurnal patterns. One thing we're trying to push forward is not just relying only on things like measuring average heart rate, average respiration rate, but also looking at other types of physiological information that we can capture via cameras, which we can't often do using contact sensors because they only have point measurement. And what you can see here is examples of magnified videos where we're magnifying on the left-hand side the pulse information. And as you can see from a video, what that means we can do is we can capture spatial information about the pulse blood flow. And peripheral hemodynamics capture a lot of information about stress. And we've been finding that these parameters that we can capture, including things like vasomotion, are often more robust indicators of stress than, for instance, changes in HRV, or at least are easier to detect via the camera. What you see here is changes in peripheral blood flow across time for an individual before some kind of stressful stimulation, during that stimulation, and afterwards. And you can see that the variability in peripheral blood flow tends to decrease during periods of stress. And also the pulse waveform. So these peaks here you see in the bottom plots are the pulse peaks. The amplitude of those also tends to pinch during these periods. And so you can see we see reductions essentially in power in those frequency ranges during stimulation. And we've found that, yeah, by measuring these signals like vasomotion and peripheral pulse amplitude, we're able to detect changes in physiology during periods of stress compared to periods of rest, and that these changes tend to be more significant than changes in HRV. And HRV is notoriously difficult to measure because it requires pretty precise information about pulse peak timing, whereas these peripheral pulse measures just require knowing the power of the waveform in certain frequency bands, which we tend to find is less susceptible to corruption from other types of noise that might be present. In order to personalize these algorithms, one thing we're using is meta-learning. And this is some really interesting work in collaboration with Xin Liu at the University of Washington, where we're using mobile devices to capture small amounts of data from individuals in order to customize a model and personalize it to them. And we can do this both in an unsupervised manner, where we use maybe post predictions from an existing model, or in a supervised manner where we collect ground truth data from those individuals in order to customize the model. And we have found that meta-learning, both unsupervised and supervised, tend to have a fairly substantial impact on the accuracy of the model, and in particular help make these models more robust to skin type, which is something that is a particular challenge in optical measurement because of the ways that cameras are designed and things like that. So by personalizing these models, we're able to reduce the error, particularly on darker skin types, quite significantly. While we don't have perfectly equitable performance here, that's something that we can push towards. So that brings me to the end of my presentation. As I mentioned at the beginning, the types of applications that we're building towards are thinking about ways that this technology can be used in contexts such as telehealth and fitness and well-being. But there are more applications that could be developed beyond that. You could imagine how some of these measurement tools could be used to make computer games more adaptive and engaging, and also potentially used in productivity scenarios as well. There's a long way to go in the non-contact physiological measurement domain, but it's a very exciting area where there's a lot of potential, both to increase the accuracy by which we can measure these signals, but also the types of signals that we can measure. As I mentioned at the beginning, we're really trying to move beyond just pulse and respiration measurement, and think about ways that we can get reliable information about, for instance, blood pressure. And this might be done through capturing pulse timing. So from different parts of the body, we would be measuring pulse transit time, or looking at pulse waveform morphology, or some combination of the two. We have a few resources that are available, including a blog post which kind of summarizes some of these concepts at a high level, particularly thinking about applications in telehealth. Some of our recent publications are highlighted there, and also those GitHub repos that contain MATLAB implementations of some of the earlier signal processing methods, which use typically ICA, PCA, and other types of source signal separation to capture physiological information from video, and also the later deep learning techniques, including the MTTS CAN model, which is implemented in Python.